To chapters 4 and 4, we're looking at polynomial functions. Everything we've done so far is could pretty much be considered a polynomial function. We just have been looking at certain types of polynomial functions. So like all of first semester, we basically used mx plus b equations, right? Or ax plus by equals c equations. So they were also polynomials. They were just polynomials to using x to the first degree, okay? Then this last chapter was all x squared, right? So our standard form was ax plus bx plus c, ax squared. So those are what type of functions? There's a cube, quadratic, right? So they were also polynomial functions, okay? So everything we've done is polynomial. It was just certain types. This chapter kind of takes care of all the rest of the types of polynomial functions. And we're going to talk about common characteristics of all of these types of equations, okay? So we're not going to go as deeply into any certain type anymore because we went very deeply into x squared and linear. This is more of an overview of all the rest, okay? So first thing we're going to do is we name them. So we classify polynomials in two ways. First, we classify by degree. So the definition of the degree is just the highest exponent in the equation or the expression. So if we look at an example, if we look at an equation and this has x to the fifth, 2x to the fourth, negative 3x, to classify the degree of the whole equation, we're just looking at the highest. So this is an equation of degree 5. Next one, again, we look at all the exponents. The highest is 3, so this is an equation of degree 3. Okay? Now, the degrees also have names, and a lot of this should sound familiar to you guys. I know earlier, you should have done this in Algebra 1, so a lot of this will be familiar, just a lot of review. You will be responsible for knowing the vocab words, though, and how to spell them, okay? So, if we have a degree of 0, okay, it looks like, this is an example of a term with degree 0, because it's kind of implied that there's 6x to the 0, we just never write it, okay? So if we had an equation like that, it would actually look like this. So $1 million question, what kind of graph is that? I don't have $1 million, so what would that be? Y equals 6 is what? No. You were vertical. It was vertical, you chose the wrong one. Horizontal, right? You were getting there, you're at least in the ballpark. So again, just remember, Y equals 6 is just a horizontal line, right? So there's it's an implied polynomial even though the x isn't written. So the name that describes that type of function or the degree of that equation is a constant. 16x to the first, or 16x is an example of a term that is a degree of 1, right? And we're used to seeing that in equations kind of like this, right? And what kind of equation is that called? What's that? It's mx plus b, very good. That's the form. What type of equation? What's the graph of this going to look like? It's just going to be a slope. Well, it's got a slope. It's just going to be a line. I'm not leading you all exactly right. It's just going to be a line, right? So this type of equation is linear. So the word linear describes what the degree is. So the degree, anything with a degree of 1 is called linear. Okay? Now, 4x to the second would give us equations, again, kind of like this, which are, what kind? Thank you. Everyone should know quadratic equations. And the graph of these look like what? Which are called, and hopefully everyone's aware of this, not just Allie, right? Okay, so yeah, anything x to the squared, if that's the highest degree, it's a quadratic equation. We just tested all of that. Okay, anything with a degree of 3, if that's the highest term, again, the equation could look many different ways. It takes the form of this. We're going to just look into that a little bit more later, but that's the basic shape. And that is called a cubic. equation, degree of 3. Degree of 4 as your highest degree is quintic. I'm sorry, quartic. All the Q's get a little bit confusing. Quartic, think quarts like 4 quarters to $1. Degree of 5 is quintic. So you will have to memorize these, and you have to know how to spell them, because you can't just put a Q and then a bunch of letters, and you choose which one you want. Okay? So if we're looking at an equation, and we want to say what the degree of the equation is, again, it helps to have them all in decreasing order degrees, and we'll get to that in a second. But the highest degree here is 3, so therefore the equation of the degree is 3, so it is a cubic equation. Next example, this is one that we've seen a ton, right? An equation like this. Degree of the equation is what? 2. So it is a quadratic. Thank you. Okay, questions about that? Very good. Okay, so that is naming it by degrees. Okay, we can also name it, we name it in another way, with another set of terms, by how many terms are in the equation, all right? So a term is just one term, I don't know what I'm going to say, but one term. If I were to make this an equation, y equals 4 is a one-term equation, okay? Y equals 6x is a one-term equation. Even this last one, which is kind of a crazy term, but even though it's 4x third, y to the second, z, that is still just one term because they're all being multiplied together, so it makes it one term, okay? One-term equations are called monomials.
Are we moving up to these?
Yes. Okay. Now, two terms, when you have more than one term in an equation, again, they have to be associated with pluses and minuses, right? Multiplication does not make separate terms, but adding and subtracting does. So like x plus 1, that is 2 terms. 3x to the third plus 6 is 2 terms. Okay, so the terms are, and you guys know this, we've used this many times, but that distinguishes terms as adding and subtracting. So a 2-term equation is called a binomial. Think like bicycle. And then a 3-term equation would be what? Try. There we go. Trinomial. Okay. And then a 4-term equation, we don't really have a fancy name, so we just call them polynomials of 4 terms. Or if there's like 5 terms or 6 terms, it's just a polynomial of that many terms. Okay? Questions about that? Okay. So for example, if we look at this, if we want to name by number of terms this equation, it's 1, 2, 3, 4 terms, so it is a poly of 4 terms. And you can, I forgot lots of questions about, do we have to write the whole thing? You can say poly of 4 terms. It's about as shortcut as you get. Okay? All right. So to name these using both, to fully name a polynomial, a couple steps you want to do. First, we want to write it in standard form. And again, to get something in standard form, that means taking care of distributing, FOILing, multiplying, combining like terms, etc. You want to do everything you can to get it as succinct as possible. Combine like terms when you can, and then put terms in order of highest degree to lowest degree. Okay, so that is very similar to the test that we just took, that first section where I had you do all the multiplication and then tell me whether it's a quadratic or not. Remember that section? That was kind of in preparation for this, okay, in the fact that before you try to name something, even if before you try to identify what type it is, you need to clean it up, put it in order, and then name it, okay? Because you might get some surprises. So, for example, if we have these 2 binomials, and we want to find out, we want to put these in standard form and name the polynomial. First, we want to FOIL, right? So just a kind of a brief review, x squared times x squared is what?
X to the 4th.
X to the 4th, right? So when you're multiplying variable with an exponent, you add those exponents, right? So when we FOIL this, first term is x to the 4th. Outside terms, x squared times negative 2 gives us negative 2x squared, right? Inside, 1 times x squared is 1x squared. And last, positive 1 times negative 2 is negative 2.
Using the exponents to add them.
When we're multiplying the same base in different powers, you just add powers.
Okay.
Add exponents. Okay. Okay. All right. So now we can combine some of these. And again, remember, combining like terms. In order to combine, they have to have the same exponent, and you just collect them, right? So what can we combine here? Let's choose.
Negative 2x squared and then plus.
Right. So we can combine these two. So we're not going to change the exponent though, right? Like it stays x squared. So we bring over this x to the 4th, because it's only one of those. Now we have negative 2x squared plus 1x squared gives us a total of negative 1x squared. And then our negative 2. Okay? So this is standard form because, again, all the multiplication's done, terms are combined, and it is in decreasing order of degrees. So the highest degree is first, and then it goes down from there. So using that, again, we look at the first term to name it. So our highest degree is what? 4. So degree is 4, so this makes it a quartic. Number of terms is what? 3, right? 3 terms, so it's a trinomial. So therefore, this equation is a quartic trinomial. See how smart you sound when you say quartic trinomial. So there can be any combination of the two types of naming, right? There can be quintic binomials, there can be linear trinomials, etc. Okay? Questions about that? Okay, so main thing you want to think about here too is don't be too quick to name. That's why on the test, I tried to stress it, that you want to show me all your work, complete it all before you try to name it, because you might get some surprises. For instance, this is kind of a goofy looking equation, but we're going to simplify it and name it. But at first glance, you would think, oh, it's going to be a cubic, right? But change this up a little bit. So how do we start to simplify that? Again, let's just use PEMDAS. Distribute, right? Because parentheses. So we want to distribute. So we get x to the 3rd. Again, x squared times x minus 4x to the 3rd. Right? And then plus 3x to the 3rd plus 2. So we're taking care of our exponents, our parentheses, and now we want to combine like terms. And we can combine what? All of the x to the 3rd terms, right? So Olivia, what do you think?
Oh, 2 is going to be by itself because they cancel out.
Exactly. So 1x to the 3rd minus 4x to the 3rd plus 3x to the 3rd ends up giving us 0x to the 3rd plus 2. But we don't have to write anything with 0, right? So it simplifies to just 2. So what kind of a polynomial is that? Monomial. And what's the degree?
1.
0.
0. So constant.
Right, constant monomial, right? See how smart that sounds? Better than what? You remember doing those? Yeah, you guys.
Yeah, I already done these, yeah.
Yeah. The biggest issue you have, that you guys have done these before, should be reviewed, but you have to come to the book.
Well, I didn't remember last one.
Okay? All right, so the next one. So if we look at this one, again, we want to combine. Raise your hand. What can we combine? Olivia?
3y squared minus y squared.
So we get
2y
two x squareds, right? Can't really combine the 3y to the 3rd. And can't really combine the y. So again, it's important when you're putting this in standard form, you want to write it in decreasing order of degrees. Okay, so you want to keep it in this order. So who can name this for me? Okay?
Trinomial.
This is degree of 3, so it would be cubic, right? So normally we say the degree first, so cubic trinomial. Okay, questions about that? All right, the next slide is about 5 of them that I want you guys to work on. 5. So this is, and I just want to briefly touch on this because I've seen this actually on like some ACT questions, whereas we name the equation by the highest degree, but actually every term within an equation can be named by its degree. Okay, so sometimes, like I've seen the questions somewhere, like given something like this, is what is a quadratic term? Okay, I just want you to be aware when you have those names for degrees can be used, you know, to describe anything, not just equations. So if we wanted to name each term on an equation like this, this would be the quartic term, okay, because it's x to the 4th. This negative 4x to the 3rd would be the cubic term. And the 8x squared would be the quadratic term. You guys get where I'm going here? So you're just using those same descriptors to talk about individual terms instead of the whole equation. So just in case you ever see this on like a standardized test asking you to use those. So this last one, I think it's a negative 24, would be the constant. Okay, questions about that? Okay. Yeah, like I said, we're not going to go into graphing these really specifically in this chapter because we kind of do an overall view of polynomials, like common characteristics that all polynomials share. And 2 of those characteristics that we talked about are end behavior and turning points. And this is actually kind of a precursor pre-calc because we cover these end behavior and turning points quite a bit in pre-calc. Okay, so this is kind of pushing ahead a little bit. So end behavior is defined as what the graph does, or actually, well, what the graph does at the end. So very technical. Okay, the official definition would be more of the behavior of the graph as x approaches infinity and the behavior of the graph as x approaches negative infinity. But we can just think about it as what does the graph do at the end, okay? To denote this, we use arrows. So it's actually very simple. There's a lot of logic behind it, but it's a very simple answer to give. For instance, if we look at this graph, what is the function doing? Okay, so what is the function doing as x gets really big? So as x goes this way, if we were Allie algebra, as x is walking out this way, what is the value? This represents the y's, right? The value of the function. What is happening to the values of the function? Decreasing, right? Going down. So we put a down arrow. Very technical. What is the function of what is the values of the function? What's happening with the function as we walk, as x is really, really little? As we go negative infinity, what's happening? Also decreasing, right? So another arrow. So the end behavior of this graph is down, down. Okay? And you can do it just with 2 arrows. You could write down, down, but we just write 2 arrows. Now the tricky part about this is I actually should have started the other way because the way you write these, it's always going to be 2 arrows, a left arrow and a right arrow, but the left arrow should describe the left side of the graph, okay? And the right arrow describes the right side of the graph, okay? So that's end behavior. So this function is down, down, okay? We're going to practice. It gets a little bit more tricky. Another term is turning point, and turning point is the point where, or actually point or points, where the behavior of the graph changes. And that can be increasing to decreasing, or decreasing to increasing. So if we look at this graph, if I was, again, alley algebra, we used her what, in range and domain and what, right? That if she's walking along here, what are the y values doing? This again is a pre-calc concept you'll thank me for later. What are the y values doing? There's an arrow going down, but what are they actually doing? If she's walking along here, what are the y values doing?
Getting higher.
Right, they're getting higher, right? Because if she's way out here, right, and this is fallen, so the y value might be like negative 100, right, when she's out here. But as she's walking up, these y values are getting higher, right? Like right here, the y value might be like negative 10. Right here, the y value is like what, 3? Here, y value is 0. So if she's walking up this way, the y values are actually getting higher, right? When she gets here and continues walking, what are they doing? They're getting lower, right? Now again, this is increasing, decreasing. This isn't something that we're definitely going to go into a whole lot right now, but you will in pre-calc. But the point is, the behavior of the y values is changing. They were increasing, now they're decreasing. Okay? So this right here is a turning point. Now what else do we call it from quadratics? Does that make sense? Kind of, okay. Increasing, decreasing is a whole nother, again, it's a very analytical concept that you'll go into more in pre-calc. And the whole arrow thing kind of messes it up sometimes, makes it more confusing. But anytime it's changing from increasing to decreasing or decreasing to increasing, it's a turning point. So let's look at a couple of these. So if I look at this example, okay, first let's do end behavior. So what direction are the y values going on the left side? Up, right? And this one's pretty straightforward because it's kind of drawn for you. So the y values are increasing as x gets really, really little, right? And what are the y values doing as x gets really, really big? Decreasing, right? Going down. So the end behavior here is up, down. Okay? Turning points. TP. How many turning points are there here? Two, right? Again, they're already noted on this example. So if we're decreasing, then we change to increasing. So there's a turning point. We're increasing, change to decreasing. There's a turning point. So there's 2. And that's all we're going to say about it. We're just counting them. Okay? Now let's look at this next one. So end behavior first. So what's it doing when x is really little? Decreasing, right? Does everybody see that? Okay, it's going down. As x gets really big, as we're walking out this way, the y value is going up, right? So down, up. So just be careful. Like the answers are really easy. I mean, they're just 2 arrows, but make sure you're writing them appropriately. You know, like you're putting the right one. Because again, I don't have much to go on grading this. So if you just switch the order, even though you meant to do it, you know, you missed it. So be sure take it that way. Now, how many turning points? 1, 2, 1. Anybody else? How many think 2? Okay, how many think 1? How many think 0? There you go. Okay, this is actually 0 because the definition of turning point is where it changes from increasing to decreasing. So this function is actually increasing the whole way, right? It kind of increases a very little bit here where it pretty much goes flat, but it's never changing from increasing to decreasing. Does that make sense? So this one is turning points 0. Hannah, you okay?
Yes.
This is analytical thinking. Okay, this is a little bit different than what you're used to. With,
It's like a slide with no hills.
It's like a what?
Everyone.
A slide with no hills?
Yeah.
Yes, yeah. If you were,
If it has hills.
if you were sliding down this right, you're never losing momentum. I mean, you might slow down a little bit, but you're never going the other way. Yeah. Okay, very good. All right. Okay, next one. So end behavior first. So what's x doing as it goes, as x gets, what's y doing as x gets really little? Up. And as x gets really big? Up. Right, so up, up. Up, down, down. Like in yoga, down dog, up dog. Okay, how many turning points? 3, right? Because here it's decreasing, then increasing, so that's a point. Increasing, decreasing, decreasing, increasing. So okay, everybody good? And now it's the fun part. Okay, so now it's pretty easy to tell end behavior from a graph, right? It's a little trickier, and actually I'm doing the same thing with my calculus students right now, so this is a very useful skill in math world. But now we're going to talk about how to tell end behavior from just an equation, all right? Now the book gives you this chart, but honestly this chart kind of confuses me, so I want to teach you all how to think about it in a bigger picture, okay? And you can do this. So if I gave you this equation, okay, we've seen a lot of these, right? What's the shape of this equation? Quadratic, right? Everybody look up at me. This is big. Quadratic, right? Is it upward facing or downward facing? Up. How do you know? You didn't answer? Lily, you answered. How do you know it's up?
Positive.
What's positive?
All the numbers.
Right, but what's the only one we're really worried about?
The slope.
The A, right? Because we learned this last semester, we confirmed it this semester. Again, if all you really need to know for the shape of this is that it's x squared, right? And that the A is positive, right? So it's going to be upward. So therefore, what's the end behavior on this? Up, right? So really, okay, so keep that in mind. And what about this one? Okay, what shape is this? Down, down, right? Because it's a quadratic, it's down, down. All right, so so the shortcut to finding end behavior for any equation is that any equation whose first term has an even exponent, so 2, 4, 6, 8, 10, 12, 25, 26, 30. Any equation whose highest term has a even exponent acts just like a quadratic. Okay, so we know quadratics so well that when you see an even exponent, you think, oh, those are parabolas. I mean, they're, that's how their end behavior is. So it's always going to be either up, up, or down, down. If it's a positive, it's up, up. If it's a negative, it's down, down. Okay, so don't make it harder than it is. As soon as you see it's an even, just think parabola for end behavior. Okay? Lily?
So then when it's odd is when it's like, say, for y2 squared, like cubed, it would be up, down.
Yes. So would you say like x cubed?
Yeah, y2 x cubed is what I
Okay, yeah. If we did this, cubic, we haven't really gone into those too much, but cubic graphs do the John Travolta, I call it. Saturday Night Fever. Okay. So it's the easiest way to remember, although you're a little young for Saturday Night Fever. But you know what I'm talking about. So any x to the third or any odd degree, 3, 5, 7, 9, 31, 93, it's going to behave like an x to the third. Okay, so if it's a positive x to the third, it's going to be down, up. Looks like this, down, up. I'm running out of room here, so it doesn't really. If it is a negative x to the third, or anything, any odd exponent, it flips.
Up, down.
Up, down. Very good. So you really only have to memorize 4 end behaviors, right? And we know parabolas already. So positive parabolas or positive even is up, up. Negative even is down, down. Positive odd, down, up. Negative, up, down. Okay? This chart, let me show you the chart a little bit. The chart, it says the same thing, only I just think it's kind of complicated. But what this says is find your first term. So find, they call it ax to the n. So let's say I had 3x to the 5th. Okay? So if this is my ax to the n, my a is 3, right? So a is positive 3. So I'm on this row. Okay? My n is 5, which is that even or odd? Odd. So then you would think about the chart, you go from A positive to N odd, and it's down up, okay? So if this appeals to you, you can memorize the chart or understand the chart. I think it will help you in the long run to just think evens are quadratics, or parabolas, odds are John Travolta. Okay? So I'm sure there's a better official name for what a cubic graph looks like, but I think serpentine is what I've heard. Okay, so let's take a look at a couple of these. So no shout-outs. Everybody think about this one first. Okay, go ahead and write the answer down, and then I'm going to answer. So 3x to the 5th minus 7x plus 12. So go ahead and just give it a shot for end behavior.
Hey, I have a question. Could you come look at this and tell me if this is kind of like a one-week from there?
Oh my god, stop. Okay, whatever.
You like shut it down.
This needs to be down.
I'm not trying to do that.
How does that do?
Yeah, no, that's not right.
Just close
Negative
that
odd.
out.
You messed up a couple of those. Okay, so I'll look at it in just a second. Okay, what, raise your hand, who can tell me?
Oh, so they're just switched?
Well, I think there's a couple things on that. Hang on. Olivia, what you got?
Down up.
Right, down up, right? Because it's John Travolta, because it's odd, and he starts out like, so think about it, because this kind of confuses me sometimes. The initial positive odd is going up all the way. Okay, so like, you know, increasing the whole time. So down up, if that helps.
So the exponent, the exponent always goes first.
You want to, the exponent tells you the shape. Okay, so the odd exponent is telling you it's one of these. Okay, and then the fact that this is even tells you, I'm sorry, the fact that this is positive tells you that it's this position. Okay?
Okay.
If it's odd, if this were negative 3, the odd tells you it's still this shape, but the negative tells you it's the flip side of that.
Okay.
Okay? Just like, so Lily, I'll pick on you this time. So this is a 4.
Okay.
So what's the shape?
The shape is just, it's even, so it's just going to be like a regular line.
Well, like a parabola.
Parabola.
Right. And it's a negative.
Yeah.
So a negative parabola goes which way? Down. So it is, so the final answer is what?
Yeah.
Down, down, right? Does that make sense? So the even tells you that they're going to be the same direction no matter what. They're either going to be both down or both up, but you have to look at positive or negative to see which way, okay? The odd tells you it is serpentine or John Travolta. The positive would tell you this way, the negative would tell you that way, okay? All right, try these next ones. Just these next two, actually. No, we'll go, yeah, we'll do all 4. So go ahead and try the next group.
Are we going there or going on homework?
You're going, we still have 23 minutes left. Yeah.
Do we just do the first one?
Go ahead and do all 4 of them. Just go ahead and look at those and just give me the, so your answer to these again is just 2 arrows. There's just a lot of thinking behind that. 2 arrows.